Today we're going to start Unit 6, and before we move forward, you might be asking, hey, where did Unit 5 go? Well, to be honest, it's a data unit, and so our scatter plots and trend lines are part of that unit. We just pulled them into Unit 4, and the other part of Unit 5, those data topics have been moved by the high school into geometry, which is good because we've rarely had time to get to them in 8th grade. So you're not missing anything. So as we start, we're going to start talking about systems of linear equations. And today we're going to learn how to solve a system of linear equations using graphing. Now, what you should have in front of you are the 6 graphs that I asked you to do to graph, both lines on the same coordinate plane. And that needs to be here because as we go through, we're going to use those 6 examples, and it makes this video go really fast. So if you haven't done that, you want to pause right now and have done that. I'm going to call it a worksheet, but it was just to make sure you had the graphs ready to go for this video. So the first one, you should have graphed the red and the blue line on the same set. And we're going to talk about what this is in just a second. So we'll come back to this one. Now, before we go back to that example 1, I just want to give you an example here of a real world example of what we're doing. We're actually going to start with the, why do we have to know this stuff? So what this is the Nintendo Switch. And I'm just saying, hey, Mario Kart 8, they come out with an example for the Nintendo. And we're kind of look at this graph and kind of see what is it telling us. So title important, Mario 8, game sales and costs. And this would be, the Switch. So we've got a green line and a blue line here. We're just trying to figure out what they are. So this I can see is money, million up to 4 million. And out here, 10, 20, 30, be careful. That's the number of units sold in thousands. So the first point we have to think about is what is this green line right here? Well, if you look at the title, one of these is going to be the sales and one is going to be the cost. So if you have 0 units sold, you make 0. That to me sounds like sales. That's the money that's coming in to, Nintendo as you sell those units. So don't forget, though, that these are 50,000, 60,000, 70,000, and so forth. Now, the blue line, therefore, must be the cost. And you might be saying to yourself, why does it start up here? Well, basically, before you even sell the first unit, you've spent a lot of money in salaries and development and all kinds of things. And to be honest, I have no idea. I can hardly imagine what the cost would be before the game starts. So, and those costs will continue as people continue to sort of update the game. If they are physical copies of the game, there are actually materials involved. So, those costs can continue to kind of go up. So the question is, this is a systems. This is what your graph should look like, 2 lines. And I'm kind of questioning what this point is right here. So basically, we've talked about this before. So this right here is the money coming in. You might remember that. And this is the money going out. And where they meet, do you remember what that was called? Hopefully you said the break-even point. So basically, if you look at this blue line, and that's the money going out, and this is the money coming in, this whole sort of triangular piece is a loss. You spent more than you made. So this is, and your loss gets smaller and smaller the more you sell. Soon as you go past the break-even point, the sales are riding on top of the cost, and this sort of triangular region, if you kind of pulled it out, is now called profit. So do you think this point is important? You better believe it, right? Because if we don't get to that point, then the company lost money. So every CEO, that's the chief executive officer, every CFO, the chief financial officer, are keeping an eye on, what do they have to sell in order to basically break even, make the money back, and move into profit. So I just want you to see that as we move forward. Today we'll be looking at some graphs, and they're not going to be in the millions and the thousands, but this is basically the same analysis that we're doing. So we're going to solve a system of equations by graphing, and you've actually already started this. Oh, by the way, it is in your book. It is chapter 7, section 1, in case you need it. To solve a system means that you're going to solve two equations simultaneously. That means at the same time. The ordered pairs that you get, that point where the two lines meet, is called the solution because it solves both equations. So if you put the x and the y into both equations, they will work. They will check. We're going to talk about that in a second. So basically, you've already started this. You need to be able to graph the two lines. So sometimes you might have to solve them for y, put them in slope-intercept form to make them easy, or standard form. And one or the other might be a better way to graph. This section is really important about accuracy. So you don't want to be sloppy. You got to use graph paper. You've got to use a straight edge, a ruler. You've got to put your points in the right spot. So sometimes one form or the other would be more accurate, and we'll see that in a minute as well. You're going to graph both equations, which you've already done 6 times, on the same coordinate paper using that graph paper, using the straight edge. And now we're going to go further, and you're going to look at where did the two lines meet. And you're going to estimate the coordinates. You're going to look at the graph and say, well, looks like they met at 2, 1. And then you're going to check that in both equations algebraically, because it's really easy sometimes to graph them and kind of wiggle a line a little bit and actually have it not be precise. So we're going to check them. And for graphing, you have to check it in both equations. So right now, you've kind of done hopefully 1 and 2. Now, if you've graphed them wrong, then they're going to meet at the wrong point. Your check's not going to work. So when your check doesn't work, either you graphed the lines wrong, you somehow read the point wrong off of the graph, you substitute them wrong. There's a lot of little things you can do wrong to sort of not have the proper solution. So let's go back to that number 1. So you should have graphed these two lines, and I'm using color to kind of show you, but this one is already in slope intercept. So the intercept is -6, rise 3, run 1, rise 3, run 1. And it's really important that you make your lines nice and long here. Otherwise, sometimes they won't meet. Don't make them short and stubby. Now, the next one is in standard form. So you could use your intercepts here. So if you cover over the y, the x-intercept would be 2. And if you cover over the x, make it equal to 0, the y-intercept is 2. And then you draw your line. And where do they meet? Well, right now, I think the solution of this system is 2, 0. Now, what I'm going to do is I'm going to check that. I'm going to put 2 in for x and 0 in for y and check it in the red. And I'm going to put 2 in for x and 0 in for y. Big mistake is to put them in for the wrong variable, like you're not thinking, so just be careful. So I do that in the red line, and I get 0 equals 6 minus 6, which is 0. And I put it into the blue line, and 2 plus 0 is 2. So they both work. I've got the right solution. That's how easy this can be. All right, so let's go into number 2. You should already have it. So these are both in y equals mx plus b. So again, use your y-intercept of -1 and then rise 2, run 1, rise 2, run 1. I kind of recommend using that slope a lot. Sometimes once you've got the first line, you can use kind of the slope on the second line until you hit the first line. I'll show you that in a second. And then the second line is going to start at +9, but be careful, remember to go down 3 and over 1. All right, so let me just go forward to show you those two lines. So what I'm saying is once I had the blue line, if I start at 9 and go down 3 and run 1, and down 3 and run 1, boom, I've hit the other line. So you can keep using the slope, which will make you feel confident about your estimate of the intersection, which should be 2, 3. You must check it in both. So I'm going to put it in the blue equation and check it. And I'm going to put it in the red equation and check it. And they both check out. So I feel 100% confident that the solution of this system is 2, 3. Okay, so here's the next one, which was number 3. And this one, you can say, hey, it's in standard form. The problem with standard form here is that one of the intercepts is not in the crosshairs. So from an accuracy standpoint, it might be better to solve it for y. So I subtracted 2x and I divided everybody by -3. And now if I plot the -3 y-intercept and go up 2/3, I'm working on the crosshairs rather than, I think the x-intercept would have been 4.5. I mean, you can still do that, but the accuracy, it's so important on this one to graph it properly that sometimes it might be easier in one form or the other to get the points right on the crosshairs, basically. And then do you remember what this line is? Okay, hey, wait a minute, there's only one variable. Okay, it's a weirdo. Now, which weirdo is it, horizontal or vertical? If you can't remember, remember that every point on this line has an x of 3. So 3, 1, 3, 3, 3, 5, and pretty quickly you can see that that's a vertical line. So basically, you should have plotted these this way. So if I take a look at my line, see, here's the -3, and I go up 2 and to the right 3, and I'm already hitting that vertical line. So my estimate is 3, -1. Now, the check for this line is stupid. For granted, it just, yeah, 3 equals 3. And the other line, I'm going to remember to put it back in the original, not what you affected, just in case you goofed it up. And I check it, and it works. So remember to graph. You can use the intercepts, which would have been tough for this one a little bit, or you can use y equals mx plus b. So it's either standard form or slope intercept that's going to make it easy to graph. Okay, let's keep going. So before we move on, there's a different kind of question we can ask. So, is 2, 1, is the point 2, 1 the solution of, a system? Now, you really don't have to graph this one. You can basically just do a check. So if you put 2 in for x and 1 in for y in both lines, and if it makes both true, then it would be a solution. So in other words, there is the top line. I put 2 in for x and I put 1 in, I do the math, and I'm like, yay, okay. So right now, I know that the point 2, 1 is on the top line. If it's also in the bottom line, it would be a solution to the system. If it only makes one true, it's not a solution to the system. And I put the x and the y in, and it's true, so that is a solution. Now, would 2, 1 be a solution to a different system? So same thing. Put the 2, put the 1, which we just saw over here, right? And now a different line, and I put the 2 in for x and the 1, and you'll see that doesn't work. So that's not a solution to the system. That point 2, 1 is on the top line. It doesn't reside on this line. So basically, if you look at these as being streets and like houses on the street, this house, 2, 1, is on this street, but it's not on this street. But here it's on both. So it's like in the corner, like a corner of two roads kind of thing. So now the weirdos can happen, and you probably saw that as you were graphing. So we can have a no solution, and that would be a system of linear equations that are parallel would have no solution. And if you weirdly go to graph it and you're like, hey, wait a minute, this is the same line, just two different ways to write it, kind of like Mrs. Woodruff and Mrs. W, or two ways to kind of think of me. You can sometimes, write two equations, not even realize that they're the same line, and all of a sudden you do. Infinitely many solutions is the answer there. Okay. And oh, by the way, this is also called coincident lines, also known as coincident lines. So you had to do number 4 and number 5, and you probably already know this happened. So number 4, kind of looking at this one's easy to graph, but this one, solve it for y, and you're going to notice they have the same slope but different y-intercepts. Here they are. And so they are parallel. If two lines have the same slope, we already know that makes them parallel. They have different y-intercepts. One is going through 0, the other one is going through -2. So they are parallel, and so you would say no solution. No check, we're done. The next weirdo would be number 5. And so this one's easy to graph. This one, not so much, right? And they're kind of hiding that special case in here. So let's just go over to the graphs. So you go to graph this one, and if you solve this, guys, you add 10x to both sides and then divide everybody by 2, your equation looks identical. So it's basically the same line. You don't check it. Every point on one line is a solution of the other. They're infinitely many. It's just calling a street by the name, like Colonel Ledyard Highway, CLH. It's the same road. All right, so the last one, I just wanted to make sure you guys love these so much. I said, I think we better make sure we remember our special cases of lines. So the top one and the bottom one, y equals 6. What kind of line is this? One of the variables is out, so it is either horizontal or vertical. My trick, again, is remember that every point on this line has to have a y of 6. So like 1, 6 and 4, 6 and 8, 6. Pretty quickly, you see this is a horizontal line. We just talked about vertical a minute ago. He would be a vertical line. Boom, they are perpendicular because one is horizontal and one is vertical. They meet at the point, shockingly enough, -1, 6, -1, 6 is the solution. To check it, stupid checks, okay? You got to put the 6 in for the y, and you got to put the -1 in for the x, and shockingly enough, it works. So just wanted to get those perpendicular and parallel, perpendicular, vertical, and horizontal lines back in your brain. Okay, so in conclusion, how do you solve a system of linear equations by graphing? The first thing you need to do is make sure that they can be graphed, that they're either in y equals mx plus b or standard form. You're going to graph both equations on the same coordinate plane using a straight edge and graph paper. Accuracy matters, especially it depends on how the lines are oriented, but sort of they usually meet. If they're going to meet in one point, there's kind of an X, if you know what I mean. The kind of tighter that X is, the easier it is to have it plotted incorrectly and get the solution wrong. So just as accurate as you can be plotting the points using graph paper, using a straight edge. You're going to estimate the coordinates of the point of intersection. So you kind of look, where do they meet? And then you have to, with graphing, you must check it in both. Because if you don't check it in both, it could make one true and not the other. So be a house on one street, but not be the house in the corner. So you always have to check it in both. So that's kind of what we're doing today, doing some graphing, finding the point of intersection, and checking it, guys. You are now being the CEO of Nintendo and finding the break-even point. More on that to come. Have a great day, everybody.